Welcome back, everyone. Good to see you in another video. For those of you who are new, my name's Josh, and in this video, we will be going over intermolecular forces in chemistry. So the big question is, what are intermolecular forces? Well, intermolecular forces, they are the attractive forces between different molecules. So I'm going to break down the four major intermolecular forces that we tend to see in chemistry, from weakest to the strongest. So the weakest intermolecular force we have is London dispersion force. London dispersion forces are also known as induced dipole forces because they have momentary induced dipoles in which, for example, you might see the two hydrogens right here. They create very, very weak bonds with each other. And the reason is because sometimes you might get electrons that momentarily move to one hydrogen atom of the dihydrogen molecule, making that hydrogen partially negative, whereas the other hydrogen is forced to be partially positive. This only exists for a couple nanoseconds in time, which gives it enough time for the hydrogens to form a slightly attractive force towards one another. However, this force quickly goes away and is subsequently replaced by another momentarily induced dipole. So oftentimes you'll see London dispersion forces called induced dipole forces, but they are only induced momentarily and they go away very quickly, which is why London dispersion forces, they are the weakest type of interaction. And they only occur between nonpolar molecules. This happens in hydrogen that I'm showing right here in this image because hydrogen gas consists of the same element, only two hydrogen molecules. So there's not going to be any differences in electronegativity, which is what makes hydrogen nonpolar. Polar molecules arise when you start to get greater differences in electronegativity, which is what we're going to start to see in the later intermolecular interactions that I'm going to be talking about. In these next two interactions in particular, the first of which starts now to get at a moderate strength, is known as a dipole-dipole interaction. And in this example here, I have acetone. Fun fact, for those of you who paint your nails, you may use acetone as a nail polish remover. And actually, as a matter of fact, we've used acetone in OChem lab as a cleaning reagent. This is because acetone is able to form London dispersion forces using the methyl groups on its side. And acetone has the capacity to form dipole-dipole interactions with its carbonyl oxygen as well as its carbonyl carbon. So it's actually going to create a dipole moment in which the partial negative charge is going to gravitate towards the oxygen, and the carbonyl carbon is going to be left partially positively charged. Note that because these interactions are covalent, they aren't going to be fully ionic charges, only partially ionic, given that the oxygen is attracting more electrons closer to where it's at because it's more electronegative than carbon. This is why I made that electronegativity video. Electronegativity is super important when it comes to determining what type of intermolecular interaction you're going to have. And in the case of acetone, it's going to form a dipole-dipole moment in which it gets the partially negative oxygen being attracted to the partially positive carbon in the carbonyl carbon of acetone. And it's going to form such an interaction shown in the image right here. We get even stronger interactions, believe it or not. And the stronger interaction comes from hydrogen bonding. A very classic example of a molecule that can hydrogen bond is water. But hydrogen bonding can occur in any of these three elements that bonds to hydrogen. It can occur in elements that contain oxygen, nitrogen, and fluorine. So oxygen, nitrogen, fluorine must be bonded to a hydrogen in order to be able to participate in hydrogen bonding. And what happens is that water, it's going to have the hydrogen group be extremely partially positive, and it's going to have the oxygen group be extremely partially negative. So much so that these bonds, they're technically a type of dipole-dipole interaction. However, oxygen, nitrogen, and fluorine, those three elements are so electronegative, so much so that hydrogen bonds are going to be way stronger than dipole-dipole bonds. That is why we classify them in their own specific category. And hydrogen bonds, they are of biological importance because it's one of the properties that makes water so crucial for us to live. This makes water very hard to boil, which is crucial when it comes to preserving the environment at the polar ice caps because this is what prevents the polar ice caps from melting so easily, given that water has a very high boiling point. The stronger the intermolecular interactions are, the higher the boiling point is, which means that it's going to be harder to break apart these molecules from each other. This is why it takes a lot of energy in order to make water turn into vapor, and it's often very hard to make water evaporate. It's because these hydrogen bonds are holding them together. So water is not going to turn into a gas that easily unless you input a lot of heat into it. And finally, the last interaction is very strong. It's called ion-dipole interactions. So the difference between the ionic dipole interaction and all the others is that you get water molecules. It doesn't have to be water, but it could be any dipole-based molecule that is going to interact with a fully charged molecule. So in this case, a perfect example of an ion-dipole interaction is when we get the dissolution of NaCl, aka table salt, as you all might know. Ion-dipole interactions are especially interesting because it's when you get dipole-dipole or hydrogen bond interactions that cause the dissolution of an ionic compound. So much so that NaCl no longer forms an ionic compound, but rather gets broken up into its individual ions. And these ions are surrounded by the said dipole-dipole or hydrogen bond producing molecule, which in this case, they're going to be completely surrounded by water, which normally forms hydrogen bonds around them. In this case, water is going to form a complex around the two ions. Around the sodium ion, it's going to have its partially negative oxygens be attracted to the completely positive sodium ion. Because the sodium ion is completely positive and the oxygens are partially negative, this interaction is going to be way stronger than just hydrogen bonding. This is why water, it actually prefers to dissolve salt, because all of the negative oxygens on the water, they're going to immediately rush over to the sodium and crowd around it. Kind of like if you were to see your favorite celebrity in public, everybody would go and crowd around them and be like, hey, welcome to the club. That's essentially what the partially negative oxygen in water is doing to the sodium. And the same exact thing happens to the chloride ion, but this time it's the partially positive hydrogen that's attracted to the completely negative chloride anion. And so when this happens, this causes sodium and chloride to completely dissociate as separate ions, and they're going to completely dissolve in water. This is why often when you put salt in water and you stir it with a spoon, it'll dissolve, just like that. I hope that this helped you guys, and be sure to like this video and to subscribe. And I will see you in the next chem video. Take care.